Yeah, I think you say too much about what I do. I mostly do control theory. I'm not an expert in any of the things that he mentioned, but I
Okay.
try to do my job in control. I'm very happy to be giving this talk today to you. Yeah, I really like this sort of efforts that you have undertaken there, and please count me in for anything that you need. Uh, so I say I come from Chile, so I think yeah, there are many common things between in Ghana and Chile, and very happy to be talking to you today. Okay, so I want to talk about control. I mean, please don't be intimidated about the title of this talk. I would like to very gentle walk you through some very basics of control theory, and then I will just use this as an excuse to discuss some topics in numerical analysis and the interplay between optimization, control, a bit of modeling, and and, and Hamilton-Jacobi equations, I would say. So here I put this title, Approximation, Representation, and Learning, because it's really it's my whole it's my own story as well, from transitioning from very classical numerical approximation of PDE techniques to a little bit of PDEs, and then uh, very simple things on machine learning. Nothing very fancy. So if you're not familiar with control theory, I always have this slide to try to explain it myself a little bit. So usually my departure point is always a nonlinear evolution equation. And yeah, you can see my little hand there, an abstract evolution equation. So y dot equal f of yu with some initial condition. But of course, what it makes this problem more interesting or more complex than a dynamical system problem is the presence of a control variable u. So if you weren't to have a control variable u, you just have the classical evolution equation. But here I have a nonlinear evolution equation that has an external control signal. This is what I call the control signal. And I use this. This is not just a simulation problem, but I use the control signal u in order to make the system do something that I want it to do. And the way that I select this control variable is through the optimization of a performance index. I will give you some very concrete examples in 1 second, but this is the mathematical framework. An abstract evolution equation that has a control variable, and I choose the control variable such that it minimizes some energy function of the system. This is known as optimal control or dynamic optimization, but somehow the techniques, if you have read a little bit, they are similar to inverse problems, also to differential games. When you have more than one control variable and they are trying to reach different objectives, not just a minimization, but for instance, a minimization and a maximization at the same time. Sometimes we talk about differential games. And when you incorporate uncertainty on the dynamics, so it's not anymore a nonlinear ODE, but could be, for instance, a Markov decision process, or you also have uncertainty in the cost. People nowadays also, they refer to a reinforcement learning framework. And what I will try to do in this universe is to use model and data-driven techniques from optimization to compute this optimal signal, to compute the signal u that will enable me to force the system into a certain behavior. That's what I call controlling a nonlinear dynamics. Of course, the way that I want to control this is in a robust way. So I want somehow that, for instance, that this u term be able to compensate external disturbances of the system. Things have to be real-time computable most of the time. So we have this mathematical abstraction where we compute things, but when things are implemented by a control engineer or an electrical engineer, these things should be able to run in 1 millisecond. So computation times are very fast. Everything has to be working perfectly before you put things in practice. And somehow the way that we use this control is parsimonious. So we're not acting like brute force over the system all the time. We're very selective on the times in which we choose to activate an external action on the system. So let me show you some very concrete examples of this. So what you see here in the middle is a project by Intel on swarm robotics, They have basically, each of these lights is a drone, is a quadrocopter, and they have 1,000 of these ones. So this is from some Winter Olympics some years ago in Korea. And you can see that the drones have coordinated themselves to achieve a certain formation in space. Here I have a little animation of this on the left. So you can see these little quadrocopters with the lights. And each one has a trajectory. They need to coordinate in space. They compensate the disturbances. For instance, they need to compensate the action of the wind, right? Because the wind is blowing and you still need to keep this formation in space. And of course, when they achieve this formation, you want to do it in a way that they will not crash against each other. So here you have a control problem. Each of these little drones is going to be a piece of this abstract system. They are all coupled together. They have a nonlinear interaction, and the U variable would be my computer, whatever that gives the instruction on how the drone has to change its trajectory. We also think, for instance, this is another more, it's like, for instance, no, it's not from last Sunday, but you can see pedestrians there. So these are humans in a crowd. And this is the typical example that shows the granularity or multi-scale behavior of these dynamics. So when you think about humans, you can think about not microscopic, but you can think about a single person and its trajectory. But of course, at that scale, it doesn't make much sense to control the trajectory of a single individual. At that scale, you are really looking at thousands of people, and then it makes more sense to try to control the density of pedestrians. So then you move from a microscopic description of the system, the same way that instead of working with atoms, we work with the air, with densities. We work with the multi-scale behavior, multi-scale features of the system. And for instance, we want to do a control of the density in some pedestrian environments. And then we model this as a non-local, like a Boltzmann equation or a Fokker-Planck equation for the density. This is the simulation that you are looking here in this plot. And these are my dynamics, and then I want to do control over this. Okay, so nonlinear dynamics, I want to interfere with them through the action of a control signal, and I want to design this control signal by solving an optimization problem. Very, very, that's what I do for a living. So this is really at the confluence between different topics. So it's not exactly clear still maybe what I'm talking about. So I'm really talking in a very abstract sense at a certain interplay between analysis and PDEs. So you need partial differential equations, for instance, to understand the dynamics of the pedestrians or the dynamics of the density, or you need to know nonlinear ODEs to understand the dynamics of these quadrocopters. And then, of course, you need scientific computing techniques to approximate these dynamics. And on top of it, the design of the control signal that I want to put into the system to influence, it's done with what we call optimization and control. So this is really, it's hard to say what this is really about. It's really about the interplay between scientific computing, optimization, and modeling. So there are like different keywords there. Of course, this is not that easy because for one thing, this cost here, this performance index J, sometimes is non-smooth or non-convex, so that is challenging from the optimization viewpoint. The dynamics are often non-linear and non-local. By non-local, I mean that really different parts of the system are very strongly and non-linearly coupled. You have model uncertainties, you have external perturbation. Think about the wind with the quadrocopters. You don't know where exactly how is the wind going to blow. You just have some margins to operate. And of course, you have the curse of dimensionality. The curse of dimensionality is a very technical issue, which is the difficulty associated to the fact that these dynamics are very, very, very high dimensional. So just to give you a reference here, we're talking about 1,000 drones in this image. And each of these drones would have probably a description as a nonlinear ODE with 12 states. So just this control problem, you will have 12,000 state variables in this system. So nowadays, what people are concerned is about the following. So how do we design this control? The classical school would say is to do what we call ad hoc design. So you have techniques, you study you know all the physics of the system that you want to study. You know all the properties, all the asymptotics, I don't know. You know a lot of properties, and based on these sort of abstract or analytical properties, you try to determine what is a good action, what is a good control signal. From that perspective, this method is very efficient with respect to data. There is no data at all. There is just theoretical knowledge about the dynamics, or you just need to know what is the initial condition of the system, or maybe you just need to know about a parameter of the system. And after that, you can work everything by hand or with a computer, and things work in a very efficient way. However, you would agree with me that this is not very automated. So now I change a little bit the system, and the situation changes dramatically. You have to start from scratch again, reading something else, because what you have just computed not necessarily will apply for the new model. Instead, people nowadays, they are looking into more advanced techniques such as deep reinforcement learning, which are techniques based on data and inspired on machine learning variations that are highly automated. So probably you have seen all these stories, crazy stories about using deep reinforcement learning to play computer games, to do the craziest things on Earth. And really, the methodology does not change dramatically from one case to the other, as long as you have a description of the system and the rewards that you want to give. The system will work itself. That's like the artificial intelligence sort of buzzword on it. So they are highly automated, but nowadays we're starting to realize that, of course, all these methods are very, very, very inefficient with respect to the use of data. So training a neural network to discover a control law, like a reinforcement learning algorithm, even if the same problem is very simple, this requires sometimes hundreds of thousands or millions of data points to do this regression, to do the machine learning. And of course, this is very expensive, because sometimes to recover the data is expensive, to treat the data is expensive, and it's also expensive not only in money, but for instance, energy consumption. And that's also like an ecological problem on how much energy do we want to blow up just by training these huge neural networks. And what I try to do for a living, basically, nowadays, is to balance a little bit of these two things. So really, let's try to use as much theory as possible from what we already know from 200-300 years of optimal control and analysis of partial differential equations, to somehow make the use of data in machine learning algorithms as smart as possible, such that the methods are more efficient. And then we're really trying to balance the world of model-driven ad hoc design with data-driven optimization, data-driven techniques. So this is a very, very rough picture of what we try to do nowadays in this sort of topics. But it's somehow the same picture for computational applied mathematics in general, I would say. In concrete, what I try to do, let me give you a more concrete example of what I do in terms of control. Let's assume that we have a nonlinear dynamical system. So y dot equal f of y, your favorite nonlinear dynamics. And then you have a control affine, which is called a control operator g, and a control function u. So you are trying to interfere in a nonlinear dynamical system through the action of this variable u. You have an initial condition, and then you are trying to do infinite horizon control. So for instance, this is the classical setting when you want to stabilize a system. So for instance, imagine some very simple example. Imagine that you have the temperature in a room, and then you want to bring the temperature constant. I don't know what's nice for you. Maybe I like 23 degrees. Let's say that I want to stabilize the temperature of the room around 23 degrees. I have to cool or to heat depending on the disturbances, on what is entering and what is coming out from the room. That will be described by this nonlinear dynamics. And then I create myself a cost such that by minimizing it, I can synthesize a control signal u that gives me what is the optimal heating or cooling profile that I have to put into the room to achieve a steady temperature. That's called stabilization, and the natural way to cast it is by writing an infinite horizon cost here in time, a performance measure that measures the difference of the state would be y minus y bar, where y bar is the reference temperature that I want to achieve. And of course, I'm paying a price for acting over the system. So I have a quadratic penalty here of the control energy that I'm spending to stabilize the system. So this is an optimization problem. If you're not familiar with control theory, the only peculiarity that it has is that the constraint here is a nonlinear dynamical system. Normally, when you study optimization, you study optimization with linear constraints, with nonlinear constraints, inequalities. Well, here instead, I have a nonlinear dynamical system as a constraint. One way to do this, and we have been doing this as humans since the 1950s from Richard Bellman, is the use of dynamic programming techniques. We define something that is called the value function of the problem. So for a given initial condition, the value function gives me the cost of the optimal strategy, of the cost associated to applying the optimal strategy from a given departure point. So let's say the temperature of the room is X. A given X, say 10 degrees. There is an optimal heating cooling profile to reach 23 degrees. And then that optimal strategy gets evaluated in this performance cost. And the value function tells me what is the cost associated to that optimal strategy. And then one thing that we know from dynamic programming is that the value function of a given control problem is such that it satisfies the partial differential equation. So maybe you got lost with my explanation, but now you can connect again to the fact that I'm going to jump from solving a control problem to solving now a nonlinear partial differential equation, which is something that you can solve even if you don't know anything about control theory. This is a very well-known partial differential equation. It's called the Hamilton-Jacobi-Bellman equation. I'm going to come back to this in 1 second. Let's believe for 1 second that we know that this is difficult, no, to solve this sort of partial differential equations. That's why we do finite elements or we do different numerical techniques, because almost never we can solve this by hand. So we have a partial differential equation, the Hamilton-Jacobi-Bellman equation, that governs the value function. So if you solve this PDE, you obtain the value function for any initial condition in this problem. And then the reward is that once you have solved for V, you can obtain the optimal control as a very simple operation that depends on the gradient of V. So the logic is the following. You write your control problem. You find the Hamilton-Jacobi equation associated to that control problem. After that, you solve the Hamilton-Jacobi equation. You recover V and the gradient of V from solving this equation. You apply it here in this expression here, and then that gives you the optimal control as a very simple optimization problem that depends on the gradient of the value function, but just as an external datum. And here, what is important is that the optimal control is now expressed as a feedback map of the dynamics. So in order to find the optimal action to take at a certain temperature, the only thing that I need to identify is what is the current temperature of the room, and I can tell you right away from solving this very simple optimization problem what is the optimal action that you should take right now. Because you have computed in an offline phase this equation, and you have stored somewhere the gradient of V such that this optimization can be computed very, very quickly. To solve this optimization is a few times, 1,000 times simpler than solving this problem here on top. Of course, the price that you pay is that in between you need to solve this partial differential equation, the Hamilton-Jacobi-Bellman equation. So my interest here, my numerical analysis interest in this whole thing is to solve the Hamilton-Jacobi partial differential equation, which is a partial differential equation that is everywhere in applied mathematics and in particular in control theory. And it's an equation that has this form. We can have a close look at this. You have like a constant lambda that is given to you, lambda times V, and then it has a nonlinearity. And it's probably a nonlinearity that you have never seen. It's not the classical nonlinearity, no? It's not a polynomial nonlinearity. It's not advection, nonlinear advection, or things like that. The nonlinearity is an optimization with respect to a parameter, the control parameter U, that appears here and appears here. So this is a very peculiar type of nonlinearity, and this makes things a bit difficult. But looking like in the PDE taxonomy, is a first order equation. You have a gradient here, you have the nonlinearity. So it's a nonlinear first order partial differential equation. People in PDE call it fully nonlinear because really this nonlinearity is a very, very peculiar one. It implies doing an optimization with respect to a parameter at every point, at any time. Every time that you want to realize this expression in a point X, you need to solve this optimization. It's written in non-divergence form. So people like Stephen, they don't like it because people in finite elements, they like to integrate, to do integration by parts. And here you wouldn't get anywhere by doing integration by parts because it's not written like divergence of something. It's really a nonlinear thing. So it is an example of a PDE where doing finite elements wouldn't get you very, very far in terms of the solution. Of course, you can do it and obtain a solution, but it doesn't need to be like that. A priori is not probably the best technique. The reward, as I was saying, this is very interesting for control theory because after you solve this equation, you record the control as what we call a global optimal feedback map. So the solution of the optimal control now is given as a function that only depends on the current state of the system. So you get perturbed, like in my example of the quadrocopters. Imagine that the wind just blow one quadrocopter to a new position that you were not expecting, and now you need to counteract this action. And the way to counteract it is through a feedback map, because a feedback map, the only thing that it needs to know is what is the current position of the system. So you just kick the quadrocopter, but the quadrocopter, as long as you can measure its position, you can evaluate this expression and obtain what is the optimal action that you have to do to recover from that position. And that's what is really appealing for engineers to do real-time control. Because in real-time control in the real world, you are going to have perturbations, you are going to be removed from your perfect position, and you need in 1 microsecond to come up with a countermeasure with an action to compensate this. Sorry. These are very important Hamilton. This might sound a very, very, very narrow topic, but believe me that Hamilton-Jacobi equations are everywhere. For instance, a conal equation you have heard for rate propagation. You have Isaac's equation in differential games. And recently, people start looking into what they call mean field control, mean field games. You will find some recent fields medalists working on these topics. These are like very fancy topics that are everywhere nowadays in PDE, applied mathematics, control, game theory. The problem here is what we call the curse of dimensionality. This is perhaps the most difficult issue about this PDE. If I ask you what is the name a common PDE or your favorite PDE, I can bet that, well, unless you work in statistical mechanics, you are going to tell me PDEs that live in a physical space. Navier-Stokes equation. Okay, in 3 dimensions, you have 3 space dimensions plus 1 time variable is a 4-dimensional PDE. And any physical model that you can think, it lives in 3 plus 1 dimensions, more or less, because you can think, for instance, about Boltzmann equation or statistical mechanics, where you can find equations that live in a bit of a higher dimensional space. Now, this PDE instead, the domain is RD, where D is the dimension of the dynamical system that you want to control. So if you have a quadrocopter that has 10 states, the Hamilton-Jacobi equation to compute the optimal control to move this quadrocopter to an optimal position is a partial differential equation that lives in 10 dimensions. If you have now a swarm of 1,000 quadrocopters, so your state space here is a 10,000 dimensional state space, now the partial differential equation that you have to solve is in a domain of 10,000 dimensions. So this thing becomes very quickly very high dimensional, because the dimension of the PDE is governed by the dimension of the state space of the system that you want to control. And it's very easy to come up with very high dimensional state spaces. The computation and all our almost all our machinery to solve numerical PDEs is meant for solving PDEs that are written in physical space. Finite elements, finite volumes, finite difference, you name it. All these methods were, at least they were created originally to solve PDEs that live at most in 4 dimensions. And now I have a PDE that lives, well, besides being nonlinear and all this, lives in 10,000 dimensions. So that's the difficulty here. For instance, if the dynamics that you want to control they are a partial differential equation itself, because, for instance, you want to control the temperature in a room, but the temperature itself is governed by the heat equation. If the heat equation, you write it as a dynamical system, is an infinite dimensional dynamical system. You can think about the Fourier expansion, I don't know, but it has infinite states. Therefore, the Hamilton-Jacobi equation associated to the control of a physical phenomenon that is governed by a partial differential equation is a Hamilton-Jacobi equation that lives in infinite dimensional spaces. So if you want to control fluid flow problems, or you want to control the Fokker-Planck equation, you are now thinking about infinite dimensional Hamilton-Jacobi equations. So here really the challenge is, how on earth do we create numerical methods that are able to tackle the solution of this PDE, this nonlinear PDE, in very, very high dimensional problem. This is arguably the most challenging problem in modern optimal control. In computation, of course, there are many other theoretical interesting problems, but if you are asking me about computations, what is a difficult problem for control engineers or for control people, is this one. You want to be able to have a numerical method to solve this very, very high dimensional equation. How much time do I have, Stephen?
30 minutes.
20? Okay. Yeah, I think I can show you some nice things. Yeah, maybe the state of the art is not that interesting to you. I will just say that people try to solve this with finite differences and so on, and they get stuck in 3+1 dimensions for obvious reasons, because the computational complexity of solving this with a grid-based scheme, it grows exponentially with respect to the dimension. So if you have 10 nodes in one dimension, you have 100 nodes in 2 dimensions, you have 1,000 nodes in 3 dimensions. If you're working in D dimensions, you have n to the D nodes, and this n to the D, of course, grows exponentially, as we have been learning the last 1.5 years. So this is really not meant for grid classical techniques. They get quickly stuck at 3+1 dimensions. But then there is a literature of people that over the last 10 years or so, they have been doing some progress on how can we derive new numerical techniques to scale up on the dimension of this equation. So for instance, using max plus algebra, using tensor decompositions, which is something that I will quickly show you now. Representation formulas that has something to do with a little bit with PDE that I hope also to mention. I will just give you a glimpse of these things, and the use of machine learning techniques, because as one success of machine learning in general, of deep learning, is that now we have a way to do nonlinear approximation in very high dimensions without blowing up the number of degrees of freedom that we need to do this regression. So that's the power of deep neural networks. Deep neural networks are objects that would allow you to approximate a very high dimensional object without necessarily blowing up the number of degrees of freedom, the number of parameters that you need to carry on this approximation. And then you have supervised and supervised learning, all the things that people nowadays they are discussing. Okay. Let's skip this. I just want to say first, briefly, I want to talk roughly introduce you on the idea on how to construct numerical methods, very classical numerical methods, to solve the Hamilton-Jacobi equation, and what can we do with what I call tensor decomposition methods. So how do we construct a numerical method for a Hamilton-Jacobi equation? The first thing that we have to we have 2 problems. We have nonlinearity and we have the dimension. Let's think first about the nonlinearity. We have this equation here on top. We need to deal with the nonlinearity. One thing is that if you want to solve this minimization, if the parameter lives in an unconstrained space, lives like in Euclidean space Rm, which the control variable is an m-dimensional vector without any constraint, this minimization with respect to u can be done explicitly, just by doing first derivative equal to 0, because you have norm of u squared here, and then you have u here times something. So the minimization with respect to u here, you can compute it just by hand. This is, of course, just optimization, undergrad optimization exercise. If I give you everything here and you just compute the derivative of this norm and there, you obtain that the optimal control, the optimal u, is just this direct expression of the gradient of the value function. So now that you have found the optimal u, you can plug it back here, and then you can get rid of the optimization step. roughly speaking. So this U star, now you plug it inside this expression here is called the Hamiltonian. You plug it back into the Hamiltonian, and now you obtain the same equation. But now, at least for my anxiety, there is no more minimization operator appearing here. I still have a nonlinearity, but the nonlinearity now looks a little bit more familiar because it's just gradient times gradient. It's something a bit nicer, I would say. It's still nonlinear, but it doesn't have this minimization argument anymore. And then when you look at this nonlinearity, now I'm not that scared, because when I look at this nonlinearity, I say, okay, but I can construct a finite element method here. The only thing is that I have to take care of this nonlinearity by doing a Newton iteration. So if I do a Newton method for this nonlinearity, in every step, I'm going to have to solve a linear problem. And for that linear problem, I can use my favorite numerical approximation scheme for a linear partial differential equation. And that's an idea that has been around for the last 50 years in dynamic programming. Hamilton-Jacobi equation. It has different names, but it's basically doing a Newton method for this equation. People in machine learning, they talk about policy iteration or Newton-Kleinman iteration for Riccati equation. So how do you construct a Newton iteration for this scheme? It's basically an iteration where you give a guess of U, you give a guess of both phase U, and then when you freeze the U in your guess, you just have to solve a linear equation for gradient of V here below. So you freeze U with a guess, you solve the linear equation associated to U. I'm assuming, sorry, lambda equals 0 here. You solve the linear equation associated to gradient V. Then with this relation here of the optimal control, once you solve gradient V, you can work out an update of U, and then the update of U, you apply it again into the linear equation. This is a Newton method. It's truly a Newton method for this equation here. Just freeze the control, solve the linear equation that is left after freezing the control, update the control, the policy, and then solve again. And you iterate this until you reach convergence, and that's the way to treat this nonlinearity here. Of course, the catch here is that now at every time, at every iteration, I need to solve this equation here. Well, this is just there is some theory asserting the convergence of this Newton iteration, but as you know, this might happen or may not. Newton iterations, they are always sensitive to the initial guess. There are ways to initialize this in a smart way. I don't think that could be very. If you are interested, you can ask me afterwards, but this is not something fundamental. The fundamental thing is that now I can get rid of the nonlinearity, but at the price that at every step I need to solve a linear equation. That's fine, except for the fact that this linear equation still is a very high dimensional one. So I'm still trying to solve a 10,000 dimensional Hamilton-Jacobi equation. The thing is that now I'm not solving a nonlinear equation, I'm going to solve a linear equation. This is called the generalized Hamilton-Jacobi equation. So maybe now you just want to simplify your life and focus on the problem of solving a linear PDE, but in a very high dimensional space. So for a gradient of V or dV that I call, this is the gradient, sorry. Given U, given L, given F, given G, I just want to find gradient of V here. And I have, again, the same problem. If I do finite differences, I'm not going to be able to solve this in that many dimensions. I'm going to tell you right away what we do now, the state of the art of this. We have been able to solve this problem up to, say, 120 dimensions, which is more or less the state of the art of what we can do nowadays without supercomputing, by using something that we call tensor decompositions. So people working on tensor calculus, they are very good at solving linear PDEs in high dimensions. The problem, of course, is that my original PDE was nonlinear, but now I'm in a setting where I have a sub-problem that is a linear high-dimensional problem, and for that I can do the following. There is this thing that dates from 2011 that is called the tensor train format, and this is the following idea. This is not very difficult to grasp. Think about, imagine the Hamilton-Jacobi equation in 2 dimensions, and you do your finite difference. How it's going to be represented? Well, in 2 dimensions, the value function, the solution of the PDE, is going to be represented as a lattice. So as a set of nodes, In each node, you have the value of the solution of the PDE. And it really, in 2 dimensions, this looks like a matrix, no? It's just a square with the lattice, with the nodes. In each node, you have the solution of the PDE. That's the way that we solve, for instance, with finite differences. But now you represent this object as a matrix, and we know from numerical linear algebra that this matrix has a singular value decomposition. So a matrix can be expressed as a sum of low-rank factors, low-rank products. Right? Okay. You can do this in 2 dimensions. Of course, this is an approximation. How good is the approximation? Well, it depends on how many terms do I take into this expansion, the singular value decomposition. Of course, if the singular values in the singular value decomposition, they have a fast decay, I can have an approximation of this with very few of these products. These are vector products, like external products. But of course, if the value function itself of the object here, the singular values, they do not decay very quickly, I will have to take many terms in this expansion. This is just the compression. It's the same when you do image compression or I don't know, a JPEG, or you do like singular value decomposition of your matrix, of your tensor, and then you truncate after a number of factors. Of course, the error that you make is governed by the number of factors in this expression that you are neglecting. Well, people many years ago doing tensor, they started thinking on how can we extend this to more to tensors. How can we extend this idea to higher dimensional objects? So for instance, in 3 dimensions, your value function is not anymore a matrix, but it's a 3-way tensor. It has 3 entries. This is how the solution, if you do finite differences for a 3-dimensional partial differential equation, this is the way that the solution would look like, your 3-dimensional lattice, and each point of this lattice you have a value. And now, in the same way that you do singular value decomposition here, you can do the same sort of low-rank expansion. Now, and of course, now you will have still one rank factors here, so you will have vectors, but you have the product of 3. How much do you save by this? Well, you have to count how many degrees of freedom here you have. You have n squared, and here you have 2 times n. If this is n by n, you have n squared nodes. Here you have n times n. Sorry. If you were to have the first 3 one, you have 3 times. But is d times n degrees of freedom, depending on how many of these factors you take. So in d dimensions, you will have n to the d degrees of freedom, which is a lot. It's like zillions of nodes if you do the full expansion. But if you do this sort of compression, now you don't have an exponential dependence with respect to the dimension, but you have a linear dependence. And this is when you read papers and people talk about circumventing or breaking the curse of dimensionality. That's what they mean. They are removing this exponential dependence with respect to the dimension with a linear dependence, in this case, with respect to the dimension. So of course, now I can solve 1,000 dimensional examples because I'm not blowing up the computational complexity of this object. At the tensor train, here is just a way to write down this expansion. It's called a train because it's really a concatenation of 3-way tensors time a 2-way tensor, a matrix here. So you can really, this full object here that is represented by a d-way tensor, so a full high-dimensional lattice, you can express it as a multiplication of these factors here. And these factors are 3-way tensors, each one of them. It's a 3-way tensor, but you do a sum over 2 components. So you have a 3-way tensor, you sum over 2, you are just left with a one-way tensor. So you do the double sum here and you do the concatenation. So this is a way to work out a compression from a very high dimensional object and to compress it like with this linear complexity and to express it as a sum of low rank factors. Of course, the $1 million question here is like the singular value decomposition. There is no magic here. You can do this, but of course it's going to be an approximation. How good is the approximation? Of course, it depends on how many terms you take in this expansion. And of course, this thing, in order to be efficient, it requires that the expansion somehow can be, the image or the object can be represented with few factors. If it has too many factors, then it's not efficient anymore, and you are back again to a very, very complex object. So the million-dollar question here is, can we characterize the class of control problems or the class of solutions of Hamilton-Jacobi equations such that we know that the value function can be accurately compressed with few of these factors? And well, yeah, this, I don't want to bore you with this, but the answer, this is sort of thing that we do in terms of research, and we have partial answers like, yes, we understand that the class of problems, for instance, linear control problems, where the matrix A has certain properties on the rank of the off-diagonal blocks, if they are well behaved, we can obtain bounds on how many terms does this expansion has such that a certain accuracy is achieved. I'm sorry, I'm just giving you like a very, very general picture because it's usually, it would take a few of these lectures to understand this. But the idea is that you have the object, you have some compression, and you want to understand if you can identify a class of problems where the value function, the object that you want to solve, has good compression. If it has good compression, then you can basically assume that the full object can be represented as a sum of low-dimensional objects. Basically, I'm trying to do here some very fancy separation of variables. If I know that the value function would admit a separation of variables, I can express it as a sum, as a product of just factors, each one going along on its own dimension, and then the complexity is going to be linear with the dimension. There is no like intertwining between the dimensions. Just to show here, maybe. So what the sort of logic that we do here is, for instance, we want to control a nonlinear partial differential equation, something like this Allen-Cahn PDE, which is a diffusion equation with a nonlinear reaction term that generates a bistable potential, so a bistable equilibrium. So you will have that the steady states are just a 1, 0, -1. You can just realize it from here, and we want to remove that structure and stabilize the temperature to the room of to 0, say. So let's say that you have this nonlinear evolution of the temperature that, depending on your initial condition, you go to 0, 1, or -1 as a constant temperature. I want to remove this and just do a stabilization of any initial condition towards the temperature 0. But this is a partial differential equation. We do some sort of a spectral approximation, so we treat it as a high-dimensional dynamical system, for instance, a 40-dimensional dynamical system, by taking the first 40 eigenmodes of this equation. And then we solve the Hamilton-Jacobi equation associated to this. So that's the logic that we use to do control of partial differential equations. We can do it. I'm just going to tell you that this is sort of the state of the art. We can solve high 100-dimensional nonlinear dynamical system with this sort of machinery. Of course, the CPU time that it takes is quite a lot. You can see here, well, not in this example. Let me show you some 2D example. So we're in the order of 1,000 minutes or something. So it's a few days this running in a computer, but this is really solving 100-dimensional partial differential, 100-dimensional Hamilton-Jacobi equation to really stabilize these nonlinear dynamics around a flat state equal to 0. What I just want to show you here as another qualitative idea is that the rank of this expansion, the rank of these blocks in my tensor train expansion, they do not blow up with respect to the dimension. And this is fundamental because it means that as I increase the dimension of my problem, I'm still able to complete things because the rank, the complexity of this object does not blow up with the dimension. So, and this is because somehow we have this characterization of problems where we know a priori that this is not going to happen. So even if the problem is very high dimensional, we can keep these expansions bounded. So the terms in the expansion, they do not blow up. They behave well with the dimension. Just let me briefly tell you what sort of things we're doing now in terms of data-driven. This is the end of a very beautiful story, because this is how far can we go with current 2021 machinery in solving partial differential equations with classical, what I will call scientific computing methods. So I'm not talking about machine learning here. I'm really talking about finite difference, spectral approximation, but working the numerical linear algebra behind because there are two steps on this. There is the step of the approximation, and then there is always like a numerical linear algebra step to solve the linear system characterizing the thing. So I go using finite difference or spectral approximation, and then in the second part, instead of using the classical numerical linear algebra, we use this sort of compression that given by tensor train or tensor calculus in general. And with that, we can really scale up very carefully up to 100 dimensions in the Hamilton-Jacobi equation. And it's really the state of the art of what we can go in terms of scientific computing for this equation. Of course, there is nowadays the other world. What if we forget all this numerical approximation and we try to think about the same problem of approximating this value function by using machine learning, using data-driven type techniques? And maybe I start closing here by giving you a very simple glimpse of what we do. Imagine now that I still want to learn this value function, this object that solves the Hamilton-Jacobi equation, but without solving the Hamilton-Jacobi equation, because you have the nonlinearity, you have the dimension. Maybe solving the PDE is not the way to go. So instead of doing finite differences or tensor decompositions, I assume a certain expansion of the value function. The object that I want to recover, V, I'm going to assume that it can be expanded as a linear combination of coefficients times a certain global basis. So I'm not thinking about piecewise polynomials like in finite elements. I'm thinking about globally defined polynomials, like orthogonal polynomials, or just the simplest monomial that you can imagine, but in many dimensions. So x1 times x2 times x3, that would be a monomial in 3D, say. And I have an expansion. So I'm saying that the value function, the object that I want to learn, is a linear combination of coefficients times polynomials times monomials defined in a very high dimensional space. And now we want to do regression. Of course, I'm going to prescribe a basis, a set of orthogonal polynomials, a set of monomials in the many dimensions that I want to solve, but I'm going to try to find this theta, not by solving a finite element or a linear system. I'm going to find them by doing regression. But of course, if as soon as we talk about regression, it means that I need data to match. So I'm not going to learn V from solving the PDE. I'm going to learn V by recovering a data set for which I'm going to hopefully do regression and recover coefficients here. Now, how do I recover data for the value function? Well, actually, one beautiful thing, and that's why it goes back to my very first slide, we try to go back to reading PD theory, to reading control theory, and you will realize that, for instance, for the Hamilton-Jacobi equation, we have something that dates back from Lax, that's called representation formulas. For instance, in the heat equation, you have the heat kernel, you have the fundamental solution. That's a representation formula for the heat equation. For the Hamilton-Jacobi equation, for instance, this one here is a Hamilton-Jacobi equation. It's perhaps the simplest case. You have time derivative of V here, and then you have the gradient. This is the classical Hamilton-Jacobi thing. You have norm of the gradient of V. It is known from Lax-Hopf that for this Hamilton-Jacobi equation, if the initial condition, this is a hyperbolic, if you have a convex initial condition, any point of the space-time cylinder, so any x comma t, you can recover the solution of this PDE, not by solving the PDE, but by solving a convex optimization problem. This is called the Lax-Hopf formula. So you give me an xt, I don't need to solve this PDE. Instead, you give me an xt, and then given this Legendre transform, this is a conjugate, this is a convex analysis. This is an object that I can compute based on the initial condition. This is just convex analysis object. You give me a point, and then I just need to solve a finite dimensional convex optimization problem, which is something that nowadays, because all the progress there has been like in image processing, for instance, we have many methods that are very efficient in doing this, and I can give you V, x comma t. That brings us to a philosophical question, because when you learn finite difference on finite elements, somehow you want to record the solution in a whole domain. You define a domain, a triangulation, and then you record the solution everywhere. Instead, here I'm going in a completely different way. I'm telling you, let's play a different game. You give me a point in xt, and I give you the solution. And I give you the solution not by doing finite elements or solving the PDE, just by circumventing this problem and solving a convex optimization problem. And this is and the thing is now I have something that is, we call it causality free, because this x, t, they don't need to be linked through a grid or a stencil or anything. You can just randomly tell me x, t's. I can use this convex optimization problem, solve it very quickly, give you the answer. And the way to go there is that now you give me a table with x, t. I can fully parallelize this. For each x, t, I'm going to solve a convex optimization problem. That's going to take me 1 microsecond per problem. And then I'm going to generate a data set. I'm going to generate a table where I will have x, t, vxt. And this vxt, each one of them was just computed by solving a convex optimization problem, which is, believe me, something that you can do in MATLAB in 1 second. It's no difficulty. And now I'm going to use this table x, t, v of xt to generate a regression that will allow me to recover this coefficient theta. So this is, in technical jargon, I'm using this xt, I'm sampling xt, I'm generating a synthetic data set for v. And now I'm doing supervised learning, but this is just linear regression because I have a linear ansatz for my v. It's a linear expansion here. I just need to solve an optimization problem here on theta to match the data of v, and I can do it with a sparse regression. So I can do it with an L1 minimization to have as many zeros here as possible in this expansion. So I put here a 1 norm in the coefficients theta, such that when I solve the optimization, I also obtain many of these thetas that are 0, so that the expansion here has just a very few terms. And this is what we're doing now in terms of regression. Of course, the story is a bit more difficult because when you talk about finite horizon optimal control, this sort of representation formula is not as nice as this convex optimization problem, but the representation formula for the Hamilton-Jacobi equation associated to the optimal control problem is what we call Pontryagin maximum principle, which is a 2-point boundary value problem. But this is something that one learns more or less efficiently to do in numerical methods when you learn like shooting method. You have, for a given point x, you need a forward ODE, you have a backward ODE, and you have an equation coupled them. So it's a 2-point boundary value problem because you have an initial condition for y, you have a terminal condition for p, you need to solve this simultaneously. You normally do this with a Newton method and so on. So instead of solving a convex optimization problem, when you go try to mimic this for an optimal control problem, you need to solve a 2-point boundary value problem. But again, you can give me a table of xt, I can decouple them. For each one of them, I can solve one of these different problems that are finite dimensional and very cheap to solve. And then I can construct a data set to do regression and to learn the value function v of the Hamilton-Jacobi equation without having to solve this high-dimensional partial differential equation. And we do this. Yeah, doesn't matter. These are all the technical details. I don't want to bore you with this because I think I'm running out of time. But this is more or less, let me tell you a little bit what sort of results we obtain. So for instance, we have a control problem here where we know that the v you can sample. For different v's, solving these 2-point boundary value problems, we can obtain these little points, these cloud points. Of course, here you see many samples. I'm not using all of them. If you were just to take 40 of these points randomly and do the regression as I was just explaining you will recover this object here. It doesn't look very good. It is not really this shape, the one that you are recovering. You are recovering something else. Then it comes what I was explaining at the beginning of the talk. The way to solve this issue is by increasing the number of data points. So now you have 120 data points, and now you recover the right shape. I know how to do this. I'm not surprised. The problem here is that I don't like the fact that I'm having 120 points because each of these points is expensive to recover because I need to solve an optimization problem. So I'm thinking, how can I come up with a numerical method that allow me to recover this picture, but without having 120 samples? Is this anything better that I can do with 40 samples? And the answer is yes. For instance, instead of doing just a linear least squares regression, do a least squares regression, but with that 1 norm penalty on the coefficients. And that will reduce the complexity of the object. It's going to be more robust, and you are going to recover a better shape. So by being smarter on the use of the generation of the data and in the sort of optimization problem that we cast, we're able somehow to get more accurate results and be more efficient with fewer data points, as if you were to do like brute force and just number crunching with 1 zillion samplings and doing like artificial neural networks and this massive machinery that is very tempting to use nowadays. Yeah, we do this. For instance, this is similar story with the sort of drones that I was showing you with the agents. So we have these little toy problems where we have the drones without control; they will just fly away from each other. But through the action of the control, we can find the signal that makes them fly. These are positions, evolution trajectories. So it flies in a certain formation, and again, we can do this. The only thing that there are two things that you need to get from this table. We get more or less the same errors here. The only difference is that it's 100 times cheaper in the number of samples. So if you do it brute force, you will need like 4,000 samples. To reach the same error, you will need about 70 samples. If you do this sort of sparse optimization using the representation formula of the Hamilton-Jacobi equation and the two-point boundary value problem, which is something that you only know if you, before going to do the machine learning thing, you were to read some optimal control book and realize what is the proper way to cast this problem. So it's really, I like this because it's really analysis and PDEs bring you some theoretical insight that allows you to do a more efficient learning phase. Yeah, I won't bother you with these details. I think this is a nice closure of whatever I was saying. We have Hamilton-Jacobi equations that arise in control. You can go like the scientific computing way and still try to use grid-based schemes, but then you have to rework the numerical linear algebra to deal with these very high-dimensional problems. Or you can go through a data-driven way where you use some knowledge on optimal control and somehow simplify your life, but still you can do supervised learning with neural networks or polynomials. So I show you here with polynomials, but you can also do it with artificial neural networks, and results are very, very similar. And that really enables us to solve very high-dimensional problems, including control of PDEs, swarm robotics like I have here. So I have here these little toys. These are robots or idealized drones trying to achieve a certain formation in space, coordinating or really control. For instance, here on top, I have control of pedestrians. So the red thing, there is a density, and through the action of the green dots, we want to concentrate the density around this circle there. So, and these are things that are very high-dimensional and difficult to compute, but with the use of these data-driven techniques or these tensor decomposition techniques, we do it very successfully. Here are the references if you want to have a read. Well, this is going to remain there in the internet for posterity. We also have some codes if you want to have a look and see what the sort of coding that we do is publicly available. And if you have any question, you can look at my website, or you can just please write to me if you have any question. I'm very happy to answer any question that you might have. Okay, Stephen, I think I'm done. Thank you. Yeah.
Okay, thank you very much. Okay, so please, if you have any question, you can ask. You can just